Nothing.
Okay. We got like 50 minutes or 10 minutes of this now.
Yeah. Well, so better that than swimming. No.
No, I probably just noticing the stand.
The stand?
Yeah.
Oh, that. Yeah, that's all the
Yeah, so we got one of those,
surface.
Microsoft Surface.
Yeah. I'm not totally happy with it, but I made my choice and I'm gonna do it.
They used to be all over you documents. There's your.
I've also checked this guy out. Morning.
I just wanted to feel you how appropriate to share this.
Good.
The window there is creating a lot of glare. Is there any way you can reduce that? If you can't, don't worry about it, but
I don't know.
I know, I didn't want to put you to.
Is that what you wanted? Yeah. Tell me when it's good. Good. That's great. Thank you very much.
That wasn't hard.
Yeah, well, I wouldn't have obliged if it wasn't.
Sir?
I wouldn't have obliged if it wasn't.
Thank you.
Okay. So I noticed you at this thing about 2 weeks ago, over at International House.
Yes.
I asked if and I was sitting back, I
Oh,
knew I
okay.
was there.
I tried
But,
to promote
Yeah,
this. I don't know if we got anybody.
well, I don't know, probably not from that crowd. It was a little stilted that.
Yeah.
in the
I
presentation.
make a suggestion. First, yeah, first group of windows there is pretty bright.
You want me to lower it some more?
Yeah.
Okay, I know how to do that. Not much I know. Better? Go on more. All the way. You got it. Okay.
I gave it 12.
Well, that could be good or bad. I like. Yeah. Well, hopefully I don't fall into that trap.
I don't expect.
Well, don't count on it. Anyways, that group was a little
Sure.
stilted and I don't think they understood probably almost no one in the audience understood what happened at trial. Pruitt LIGO, which, but you know, I mean, it was a test of the aerosol dispersion. Their concern was a dirty bomb. There was no zero radioactivity. It was with things they could track, which was cadmium, zinc, telluride.
Right.
It was zero radioactivity. But because the test was associated with radiological dirty bombs, that fear, it got folded into a radiological issue, which it's not. There might be a health issue, but it's due to the cadmium zinc telluride, which
Yeah,
is
well,
a microparticle, and it can cause problems, maybe cause
yeah,
problems.
cadmium's not good for you.
Yeah.
Well,
Anyways,
yeah, I mean, under the umbrella of our government poisoning us.
yeah.
No, that's not certainly
Well,
not
yeah,
radioactive.
one of the many mistakes that our government has made,
Yeah.
but it's not, it can be in the same class of things as, you know, government missteps. It shouldn't be in the same step of people worrying about the radiological
No.
health issues.
No,
And that's the conflation, I think,
Yeah.
that was happening.
but, people being experimented on.
Yeah.
not
Well,
really.
it happened a lot more, and it was a sign of the times. It was, that's what people were worried about then, in fact, actually now too, but in different context, but they wouldn't do the test now, at least in this country.
Yeah,
All right. All right. I think we should get going. So this is the second lecture in the Saturday Science series on Oppenheimer. There was a roundtable that preceded all of this directly related to the movie, but these aren't. This has to do with the science that he was involved in, and this talk is different from the other three in that nothing I'm going to talk about here was science that Oppenheimer himself initiated, that he was responsible for generating. On the other hand, he oversaw everything I'm going to talk about today. He understood it all, and that was a substantial lift and required someone of his intellect. So I'm not going to talk about his science directly, but stuff that he oversaw. Come on in. This, I was at Los Alamos just a few months ago. This is a nearby mesa. And as you drive up there, I took that picture. There's Oppenheimer. Why doesn't this go? Now I'm going to be talking about bomb science, and I start here with a quote from Victor Weisskopf that says, "Compassion without science is ineffective," and the second part, "Science without compassion is inhuman." And in the present context, if you want to, if one desires to limit proliferation, nuclear proliferation, it behooves you to understand the science and technology that you want to limit the proliferation of. And corollary to that is compassion is rarely assisted by ignorance. So we should know what we're talking about in terms of these weapons. So that's the lift for today. And actually, you should buckle up because there's a lot of science coming your way pretty quick. The outline looks like this. And by the way, as I say, Oppenheimer knew all of this. Actually, I probably should have said 46, with one exception, and I'll make that clear when we get there. I'll start with a nuclear science primer, chart of the nuclides. It's the playground for nuclear science. I'll talk about masses and binding energies. First cut on fusion and fission. So that's fission 1. I'll come back and spend more time on nuclear fission. Energetics, something called the facility index X. Superfluidity will come in here in an interesting way. That this was the one thing that they didn't understand at the time, and it's actually quite interesting and still a topic for today. And then we'll get to the weapons primer, the types, the components, and I'll, in the process, tell you about how the natural isotopes of uranium, 235 and 238, how they differ, and how the produced isotopes of plutonium, 239 and 240, are made, and how they differ, and how they differ is exceedingly important. And I'll finish up with a few words on the German nuclear effort and the Allied Alsos mission, from which we learned what they knew. All right, so first some history. I'll start with Fermi's group in Rome. They worked on a street Pennispera or something, so they were called the Pennispera boys. And they misinterpreted, they actually were studying, they had fission going on in their lab, but they misinterpreted it. And in fact, he won the Nobel Prize for this misinterpretation. And I think if there's one way to annoy someone, it must be to give them a prize for something they did wrong. He made almost no mistakes, certainly thereafter, and maybe this is why he made almost no mistakes. But anyways, he won a Nobel Prize for misinterpretation of fission. The Anschluss happened in 1938 in March. The discovery of fission was in December of that year. Lisa Meitner, who had to flee Austria with her nephew Otto Frisch, she understood fission right away. She wrote a note to Nature, but Meitner, through her nephew to Niels Bohr. Niels Bohr came to the United States and presented the discovery of fission at George Washington University in early 39. The issue, and the primary issue, was how many neutrons are generated in fission. Fermi got a low number, the French got a high number, but by the mid-1939, all, including the Germans, knew that fission produced about 2.6 neutrons in every cycle. And I'll explain why that's important later. The French also got very close to what's called a homogeneous nuclear reactor. Fortunately, they stopped publishing everything they were doing, and they were invaded not too long after. So the French work stopped. Bohr and Wheeler, two very famous theorists, published a theory on nuclear fission and understood the difference between the two isotopes in September 39. France and England entered the war essentially at the same time. At that, just a little later, or basically at the same time, Szilard convinced Einstein to sign a letter that he wrote, delivered to an economist, Alexander Sachs, got to FDR, and things started to happen. By the way, the local history is our high current cyclotron was running just a little after that. In England, a German refugee, Pyrrhus, and this same guy Frisch, who are now at Birmingham, they understood a bomb could be built. And they did calculations. They were probably the first people with that detailed insight. And the English formed something called the Maud Committee. Through the French to the English to all the Allies, we knew why the Germans wanted B2O, heavy water, from Norway. Germany occupied Norway in the spring of 1940. A well-known Harvard chemist, George Kiskakowski, suggested a way to separate uranium-235 from 238. At the same time, Lawrence in Berkeley suggested using his cyclotrons to do it. So people were worried about separating the two isotopes in 1940. June 1940, element 93, that's one above uranium, was discovered in Berkeley. And then in January 1941, plutonium was discovered, and I'll tell you that story there. Pearl Harbor was at the end of that year. Okay, picking up with Pearl Harbor, just a little, so that's just in the new year. Compton convinces Mallinckrodt to extract uranium from Belgian Congo ore. That's the local story. And we are dealing with some of the consequences of that today. A mathematician who was in the chemistry department at Caltech, a guy named Richard Tolman, suggests that maybe to assemble a critical mass, you needed implosion. Nothing much happened at that point, but a little later, after von Neumann did some initial calculations that he relayed to Teller and Teller to Oppenheimer, that got going, and these people were involved, including this guy, Kiskatowski, because it had to do with high explosives, chemical high explosives. Now, they were actually running in Los Alamos, or people were there working before this, but it was formally formed at this late date. The local input was this guy, Lewis Hempelman, came from the med school and ran the medical services at Los Alamos. After the war, a number of people came to WashU, including this guy Kennedy, who will come up later in the talk. We knew the Germans, why they wanted D2O. The Allies destroyed it and sunk all the D2O in February 1944. This meant an easy way, a relatively easy way of getting a reactor was stopped. Okay, they had to go a different way. In the US, there was a big problem understanding the density of plutonium. I'll describe why that's important. It was resolved by Los Alamos chemists and metallurgists. Some of the group came here after the war. And a way to purify plutonium was developed by Art Wall. I'll show you a picture of him later. And it proved really exquisite at removing one problem, light element impurities, which would have caused a problem. However, almost at the same time, people realized that the way to assemble a critical mass of plutonium had to be completely different from the way the uranium bomb was made. And I'll explain why. Compton accepted the chancellorship before Germany surrendered. Everything, the mental attitude of many people working on the project changed because that was the fear that Germany would get there first. The Trinity test was July 16th. What was it? 3 weeks later, a uranium bomb was dropped on Hiroshima, a plutonium bomb on Nagasaki. In between those dates, Russia declared war on Japan. So they were on their knees at that point, really on their knees. Russia finally declared war. Japan surrendered. And in fact, after that, Russia occupied 4 islands, the northern territories of Japan, which they still occupy. Then the formal end of the Pacific Theater War ended in the signing on the Missouri battleship a little over 78 years ago today. And then a little bit after that, some chemists came here to watch you. Okay, so here's the nuclear playfield. Atomic number of protons going up, number of neutrons going to the right. Most people are familiar with the concept isotopes, fixed Z, different number of neutrons. There's an equivalent term, isotones, for varying number of neutrons, but fixed number of neutrons. And there's something very important, isobars, which is a constant number of neutrons and protons combined. That's a backward sloping line of 45 degrees that have an equal number of the sum of neutrons and protons. Now, along this line, there's the important way to view this plot is to imagine a third axis coming out at you, and that this is the minimum of a valley. A valley here, valley here. This is what's shown over here. Let me put it, and then you can decay down one side, and it's called beta plus. You can decay down the other side, it's called beta minus. If I put it in place, it looks like this. So along this line, you'd have mass going up to one side. You can slide down this side towards stability, this line here. You can slide down this side towards stability and be through beta minus and be on stability, which is this gray line. Okay, so that's our territory. Here it's shown again. There's beta minus on this side, so it's sliding down the slope to a river valley, stable down here. That's these black dots. And you can decay down the other side, that would be beta minus. Again, proton number going up, neutron number going to the right. Alpha decay, which we'll come back to need at one point later on, is a change from a parent to emitting something, emitting an alpha particle, which is the helium nucleus, 2 protons and 2 neutrons. So on this plot, you go down 2 and over 2. So it's a little diagonal cut through here. And they're not really relevant for this talk. Is gamma decay, which we're in one of these squares, but in an excited state, and it decays to the ground state. We're not going to be dealing with that. But 2 things we will deal with is fusion. Say you take 2 things way down here, heavy hydrogen, that's deuterium, so it's 1 proton, 1 neutron, and triton, which is very heavy, 1 proton, 2 neutrons. They can get together, form a helium nucleus, emit a neutron, and emit a lot of energy. Don't worry about the units, that's a lot of energy. Fission take something, so that's coming from here, going a little higher. Fission is going way up here and coming down, making two pieces, uranium plus a neutron, making two pieces. But this is, I didn't want to write a non-integer, but this is number 2.6 I talked about earlier, and a crap load of energy. Okay, so this divides into two pieces and gives you the energy for that we're going to be talking about. Okay, so that's fission going from here down to there. Okay, now you have to get a little technical. Let's say I want to talk about the mass of something. The classical view would be I want to add the masses of all of the things that make it. And if I take the mass of all the things that make it and I add them up, all the parts, I'll get the mass of the total. That's almost right, but not quite right. Because when things come together, they can be bound. And that binding energy can be significant. Let me give you a case where it's not. So let's take a proton and an electron out at infinity, and I bring them together. That makes a hydrogen atom. What's the difference between the sum of the mass of the proton and electron and the two items together? That difference is only 1 part in 10 to the 8. Okay, so I take the mass of a proton and an electron, and there's no nuclear binding energy. There's no nucleus there other than a proton, so it's that term is 0. And this binding energy of the electron to the proton is a tiny number compared to these, and I'm using mass units and energy over c². So I'm using Einstein here. Now, so this is very small, but now let me make a different statement. Let's say we want to build carbon-12, an atom of carbon-12. It's got 6 protons, 6 neutrons, and 6 orbital electrons. So those are the constituents down here: 6 protons, 6 neutrons, 6 electrons. I add that up, and it gives me this many in whatever, in these convenient units. Okay, so it's that much. Then I want to look at the binding energy. And that binding energy is 1 part in 120, which means that you lose a little less than 1% of the mass. Now, that may be a little bit hard to grasp, so let me give you a mental image. Let's say you line up 120 people, and they're going to go into a party, and the party is on a scale. Okay, and to go into this party, you have to get your weight taken. Okay, I'm going to skip the difference between mass and weight. So you have to get your mass taken as you walk in, and you can imagine two flavors, 2 types of people walking into this party if you want. Okay, so you line up these people, they go in, they get masked, and they go into the party. Okay, and 120 go in, but then you measure the mass of the people, and they're all in. And then you measure the mass of the people on the party floor, and you find it's 119. Did one sneak away? No, you take them all out, you find 120. You put them back in, 119. That's the binding energy. Now, energy is conserved. That's energy that's emitted in some form. But in terms of mass, it's like you have a party mass. Wouldn't that be nice? You go into a party and you lose a little less than 1% of your mass just by going into the party and having your friends. That's this binding energy. Okay? So that's this energy binding energy I was talking about earlier. That's this. Right? That's this term. Okay. So each of the participants, each neutron or proton, when they get into the party, they lose a little less than 1% of their mass. And this is this energy loss that I'm talking about, this binding energy. And in terms of the party size, it has a curve that looks like this. So this right where this arrow is, right around here, is about 0.8 of the total mass, the mass of the nucleon. By the way, alpha, this bump right here has to do with a particular quantum effect associated with alpha particle, and alpha decay occurs when this binding energy crosses that point. But the lesson here is the binding energy goes up, the mass goes down, and energy is conserved, and so energy is released. That's lesson one. Lesson two, the periodic table, that item, would be a god-awful mess if we use the neutron mass or the proton mass as our mass unit. We don't. We use something called the atomic mass unit, which is not the mass of the neutron or the proton. It's the party mass. It's the mass of those things on average inside the party. And without that, the periodic table, all those mass numbers that you see up here would be very difficult to understand. Okay, so fusion and fission. Fusion starts down here, and I do indicate what the sun does, and there's been a lot of news about a facility in California, NIF, that does a different type of fusion. And it is not what happens in the sun. But in the sun, you start down here, and you go into this peak, and NIF does the same thing through a entirely different set of reactions. Either way, you get a fair amount of energy. So that's fusion. From here to here, binding energy goes up, mass goes down. Fission is the party is two, so here you're suboptimal in party size. You're alone. That's not a very nice party. So you join a party, your binding energy goes up, mass goes down. Energy is released. Fission, on the other hand, the party's too big. Okay, it breaks into two parties that are more optimal. Okay, so that's what fission is. And when it does that, it releases, now I use 3, the average is in between, the 2 and the 3 I used previously, 2.6. It releases 3 neutrons, and one of those neutrons can come around, find another fissile target, and go to another reaction, and a lot of energy is released, about 10 times more than in fission per reaction, fusion than reaction. So one of these neutrons can come back, and so the fission is a free neutron multiplier. Okay. Now, it's not generally understood, but in fact, most of this periodic table is what's called metastable. So you take something like tellurium, element 52, and actually it is energetically favorable for even at that point in the periodic table for that element to break into 2 pieces. So you can imagine tellurium up here and 2 irons down here. So there's a big energy gain, decrease in energy. It's like flowing downhill, except with one problem, for even something in the middle of the periodic table to go to 2 smaller pieces. The problem is there's a big barrier in between. There's a barrier that's so large that tellurium is stable for all intents and purposes. Okay. Cannot get through this barrier. So this is where most of the periodic table is. This, by the way, is called the saddle point. Imagine a topology where you're in a hollow. There's a mountain pass you have to climb up, and it's even higher going a different path, and then you can go down. But this is so large that it doesn't happen naturally for most of the periodic table. The periodic table ends formally when this barrier goes away. Now let's deal with some specifics. Let's take uranium-235, add a neutron. We get 236, and it breaks into 2 pieces, and there are 3 neutrons. Okay, one of these can go around, start it again. That's the parent. Those are the daughters. The difference is this energy release of, in these units, a little less than 200 in these units. And so that's from here to here. That's this black line. The barrier height is this red line, and for uranium-236, it's about 5 in these units, so it has to go, so get this mountain pass that you have to climb up. On the other hand, and it's higher for 239, which would be 238 for a neutron. So this barrier goes up. And if you absorb a neutron into 235 to make 236, the excitation energy, the energy the neutron brings in due to a pairing effect, a quantum effect, is larger than for 239. So the difference between 235 plus a neutron going to 236 and 238 going to 239 is that the barrier is higher for 239 and the excitation energy, the energy rattling around in here, is lower. So for 235, with the lower barrier and more energy rattling around in here, it can sometimes get over the barrier. And then when it does, it can harvest the energy from here to here. It can slide all the way down. Okay, John Wheeler looked at this problem and he created what's called a fission instability index facility, called it facility. And the way to think about it is that you have all these protons in the party, and these protons don't like each other. They want to run away from each other, but they're held together by the nuclear force, and it's like a surface tension. And the surface tension tends to make things spherical in the absence of gravity. Like shuttle astronauts drinking water, they squirt some water out and see a little droplet going around like this, and getting all these drops. Okay, so surface tension wants to minimize the surface, so it tends to be spherical. And so that is your initial state. If you deform it, you create more surface area. And so I'm going to put that in the bottom here of this facility index and down here. And the Coulomb energy is in the numerator. You increase this proton-proton repulsion, that makes this X large. You increase the surface tension, and that tends to bring it together. Basically, he said that fission will win. It will run apart, break apart, if this instability index is greater than 1. So something will spontaneously fission if X is greater than 1 and less, and if it's less than 1, you got to give it a kick. Okay, so you can quickly deduce with a little math that this facility index should increase with the number of protons squared quadratically, so that's quick, and decrease with A. So as you go up the periodic table, Z is increasing, or if you go this way, you're in what's called an isobar, you're also increasing Z, so this facility index increases. If you go this way, it will increase because Z is fixed, that's an isotope, but the number of neutrons is going down, A is going down, this is getting larger. So these zeros all indicate increase, the direction in which fission will increase. Okay, now here's the thing they didn't understand at the time, and if they did, Oppenheimer probably could have won a Nobel Prize if he jumped on this. There's another difference between these isotopes, and it's indicated this way. These are a set of quantum levels. Don't worry about how they're calculated. Each of these lines can accept, say, two protons or 2 neutrons. It doesn't matter the details, but some go up and some go down, and these lines intersect as you get more deformed. So in fact, as you go this way to get deformed, if you want to go in a minimum energy path, you have to, the 2 particles have to move from one quantum state to another quantum state. And that'll happen in one case that I'll talk about in a minute. But let's imagine there's an odd particle here in a state that these nucleons want to jump into. So after this point, these 2 nucleons are those, but they're not in the same level. The same level is going up. This level is going down. And so they've jumped from this level, which was going up, to this level, which is going down, because that's the lowest one. But if there was already a particle in this level, that transition gets blocked. Okay, so why is this relevant? This is the case for plutonium-240. It's even. There's an even number of neutrons and protons, and this can march along to fission. And this is in fact why you have to have an implosion weapon. I'll talk, get that detail in a little bit, but this is why you had to have implosion. And over here, whoops, I need to go advance one more. Plutonium-239 does not have this spontaneous fission because there's an odd this is an odd number of neutrons, even number of protons odd here. I'll show you that in a minute. And this transition is blocked, and so it doesn't progress towards fission. So this they didn't understand. I'm a little surprised Teller didn't, but anyways, it's understood now. So now we get into the fission finally. That is the background. You ready? Okay. So fission, expose a neutron. This is induced fission. Neutron to something with high X. Now, if it was X above 1, it's going to fission on its own. If it's a little below 1, you can nudge it by throwing a neutron at it, giving it some excitation energy. In other words, the barrier is not so high that you can't overcome it by giving it a little more, giving it a kick in the pants with the neutron coming in. Okay. You'll get 2 fission fragments and a few neutrons. One of those neutrons can come back, maybe more, and find another fissile ready to fission nucleus if you give it a little kick, and start another one. We'll call that a generation, where you can have one run and then the neutron progeny can initiate another generation. So if the number of neutrons is greater than 1, you can have a sustained nuclear reaction. If it's less than 1, there's no possibility. Okay, that's like less than 1 is a fertility index of 2. Okay, so if you have a fertility index less than 2, your population is going to decrease. Okay, so it's not 2 here, it's 1, because we don't have the 2 genders. So Fermi thought it was too small for this to happen initially. The French thought it was too hot. Doesn't matter, they thought it was large enough. They got very close to running a reactor, what's called a homogeneous reactor. They stopped publishing. Good. Okay. This K index is the number of fissions in the n+1, the next generation over the last generation. Okay, so if this K is less than 1, things just decay. It's like a population decline if the fertility index is less than 2. Okay, if K equals 1, it's steady state. You may have more neutrons produced, but only 1 on average comes around and makes the next generation. That's steady state. That's what you want in a nuclear reactor and what Fermi achieved. If it's greater than 1, you have a conflagration. In other words, you have a equivalent of a population bomb. In fertility index greater than 2, things just grow. However, you don't really have a conflagration unless you have that and many generations. Because if it just goes for 1 generation, well, okay, you got an increase, but didn't make an explosion. Okay, so you have to have enough time for where K is greater than 1. So it's not just that K is greater than 1 for an instant. Well, that might be long enough. But the point is, it needs a time long compared to a generation time. So you have many generations. Okay. So this is if and only if K is greater than 1, you can have an explosion, but if and only if K is greater than 1 for a time long compared to the average generation time. In other words, you need many generations. Now, it was deduced at Los Alamos that a critical mass, I don't know why it's way down here, that sign, is given by this equation, and the lambdas are mean-free paths. It's basically how far a neutron has to go from its production site in one generation to its absorption in another generation. How far does it have to go? And it's inversely, it's proportional to that to the 0.4 power. It doesn't matter. Let's just say that was half. It's turns out that the critical mass is proportional to the density of the fissile material inversely to the square power. Okay, so if you can somehow, people sometimes say, well, why don't they just say what the critical mass is? You read this with the critical mass. Well, it actually depends on density. So to be specific, this is it's actually about the right size for uranium. A little bit too large for plutonium at a certain at the normal density. But if I took the same amount of material, let's say this is subcritical mass. So let's say it's less. And I could squeeze it, it'd be a lot harder than this, and got this, where this was my initial, this would be a critical mass. Same amount of material, but different density. Okay. So if I could squeeze this subcritical density into this size, I'd have critical density, the critical mass. So anyways, that was understood at Los Alamos. And there are some other factors in here. In the denominator, you have the number of neutrons minus 1, which is the steady state, and that's also squared. So if you have more neutrons generating fission, then the critical mass goes down. Okay. So this is a relevant equation that was, it's actually, most of this you can find in a very well-known primer that was discussed at Los Alamos fairly early on. It's in other things that are common knowledge. Now there's another term in here, this T, and that has to do with the tamper. So what is a tamper? Let's say you have the fissile material, you get above a critical mass some way, and neutrons are being emitted, they can come out. Then you get them reflected back in to get back into the game. Okay, that's this tamper. And if you have the tamper, then you can reduce the critical mass. So there's a tamper issue in here, and I'll show you how that goes. Let me see, is there something else I should say there? Oh yeah, a dud. I remember, it's probably 10 years ago now, North Korea had a explosion, but their first nuclear attempt, but it was a dud. They found the Earth in their way to make it. The next ones weren't, but the first one was a dud, and pretty clear to those of us looking at it that it was a dud. And what happened undoubtedly was that there was neutron flux prior to assembly. So what I mean by that is, let's say you have, in this, the way that it works is logically two subcritical masses, they're together, or one that looks like this, but it shrinks, you'll see it by implosion. But you have two pieces that are subcritical mass, and then you do something, it goes above the critical mass. But you don't want this to be fissioning before you start. So if there's fission going on before you assemble, then you have you have pre-detonation. It starts to go before full assembly, and that very much weakens the explosion. So you'll get a dud if there's a substantial neutron flux prior to assembly, okay, pre-detonation. Or if there's not enough generation, you've got to keep it together for enough generations. Okay, so review. In a reactor, you want this K, generation to generation to generation, to be essentially 1. And you design it so that you can keep it very close to 1. And if it goes a little above, you can reduce this K. If it goes a little low, you can increase the K. And you want to be able to adjust the generation to generation time to be sufficiently slow so that you have that control. And that's what happens in commercial reactors. So you want this generation time slow, and in fact, you generally thermalize the neutrons and slow them down. That increases this generation time. But there's something else that I won't go into this, even increases it more. But in a bomb, you want K greater than 1. You want the generation time to be fast, and that requires that you don't have thermalization. Slow down the neutrons. So in either case, you need to avoid neutron absorbing material. Okay, because if you have a lot of neutron absorbing material, they'll, even if you emit 2.5 neutrons, the neutron absorbing material will suck that up, and you won't even have one that can go back and initiate the process. So here's some numbers that have to do with, imagine these numbers are just the neutron consuming diet of these elements. This is how they eat neutrons. And hydrogen is sort of neutral, but deuterium, beryllium, carbon, and oxygen, really, these are very small numbers. They're tiny. They don't eat neutrons for lunch. They just let them go by. But boron, cadmium, and xenon very important for what happened to Chernobyl, have huge neutron diets. They'll just eat neutrons eat them all up. So if you have any of these things around a reactor or a bomb, you won't be able to get K large enough to even sustain. And in fact, cadmium is used to control reactors. You put a little cadmium in and you decrease K. All right, you can do the same with boron. Boron plays a big role in the German failure. Okay, so to maximize K, you need to increase the number of generations, and that's what the neutron reflector does. This tamper, you have something around, some neutrons go out, they come back in, and they get back into the game. That's what the tamper does. Okay. Now this spontaneous fission thing. So in summary, multiplication should start crisply. It shouldn't be on a burn before you start, and it should persist for many generations, not having this slow burn. Okay, so 2 weapons. Little boy, initially a variant of this was called the Thin Man after Dashiell Hammett's novel, but they changed it to Little Boy. And what happened is there's a piece of uranium at one end, there's another piece of uranium as at the it's not too far from it, but there's an explosion, and the explosion sends a pressure wave and pushes the 2 pieces together. It's a little more complicated than this. One of the complications I'll show you, but it assembles 2 pieces that are subcritical, makes a piece that is critical. Doesn't change the density too much, but the sum of the 2 masses went from sub to above. The efficiency of this weapon this was what was used in Hiroshima, was quite low. Only 2% of the uranium fission, and it worked on 90%, I think it was, uranium-235 enrichment. Okay, so that's type 1, and for reasons that I'll describe, that will not work for plutonium. And for plutonium, you had a core of plutonium, but surrounding it, you had high explosives that were triggered simultaneously and sent a blast wave in and compressed the plutonium very much. Didn't quite do it this much, but very much taking a mass like this and shrinking it to the same mass, but at a smaller size. That was not a hollow core, but now they're hollow core. Okay. And so that's the 2 weapons. Gun type, and implosion. So start up here in our binding energy, come back, more neutrons, and so forth. Okay, now here is the schematic view of a tamper. So neutrons will that are generated here will often bounce back, get back into the game, and initiate more fissions. There's a tamper also in the implosion weapon, but it's a different design. Whoops. Okay. Now there's another feature that's included in addition to the tamper, and that's an initiator. And in these weapons, they had a plutonium, polonium-210 source and beryllium on 2 foils, and they were crushed in between. And when that happens, it gives a burst of neutrons. So when these came together, you got a kickstart of extra neutrons when the 2 pieces crammed together. Okay, the Germans knew about the isotopes of uranium. So here's uranium-235, dig it out of the ground less than 1%. Uranium-238, dig it up out of the ground more than 99%. And they knew these half-lives. This half-life of uranium-238 is, by coincidence, almost the same as the age of the Earth. So the Earth has lost half of it in its existence. More has been lost in 235 because its half-life is less. Okay, so, but they didn't know about these plutoniums, which we're going to talk about. Here's 238, which was the discovery, not relevant for weapons. 239 makes a good bomb, but 240 makes a dud. And that's important to understand this history. So those two are bomb material. They absorb a neutron and go to these even cases. So when I said dud, what I meant was if you start with 240, you get a dud. But both of these cases, these are the proton numbers even. They accept a neutron number. They go to even numbers of, so this is an even number 244. This is an even number 246. So it starts off with an odd number of neutrons. When they accept a neutron, it goes to even. Everything is paired up, and that greases the fission, as I said in that plot earlier when I was talking about superfluidity. All right, so a new weapon is that employs fusion. It's actually quite complicated. First, they do have a plutonium core. It's hollow. There's an implosion and an elegant lens system to compress the plutonium pit. The pit is also suspended. It's not right next to these high explosives, and that gives some time for a shock front to develop. Compresses this. Actually, inside of here, there's some deuteron and triton, so it does a little bit what was done at NIF, gives you that extra little kick and another neutron. So it's like an initiator inside, but it also increases the yield. Oh, I should have mentioned that the Nagasaki weapon was more like a 20% yield. Okay, so it's 2% in Hiroshima, 20%. And that's because they had this implosion logic. Okay, but then in a thermonuclear weapon, you also have this secondary, which involves both fusion and fission in a complicated system, which is described here. But this whole thermonuclear type weapon, which is can be 1,000 times more than Hiroshima and Nagasaki destructive power, is, if you look at it all together, it's like fission, fusion, fission, fusion, fission. It's a set of fusion and fission processes feeding off of one another. Okay, now the difference between uranium-235 and 238. So this is, if you throw it, this is a probability running up on this axis, and this is for 238. First of all, I gave you the percentages earlier. 235, less than 1%, 238, almost more than 99%. And they're slightly radioactive, and they decay by alpha emission. So imagine a bucket of uranium, and there's a big valve, and it's decaying by alpha. Actually, it's still a small leak because it lasts the years of the Earth, but still, the major decay route is alpha. But, and going over here to the probabilities that what happens when you expose them to neutrons, the red is
nothing happens, it just goes to 239 and sits there, that's the red. And this is energy going up, unless you hit the U-238 hard with a fast neutron, higher in energy than you usually get in the fission process, it will just stay 239. But here, the black in 235, the black, which is the fission cross-section, is larger than the nothing happening cross-section off through the whole energy range. This line, green line on the right, is the average energy for the neutrons that are produced in fission. So not much happens in 238 if you have it, it just goes to 239, but 235 mostly fission. But going back to the native elements, native isotopes, not exposing them to neutrons, they just decay by alpha emission. And there's another valve over here, spontaneous fission. So if I have a thing of uranium-235 or 238 in my hand, it will be alpha decay. It will not be spontaneously fissioning. That's important. So why do I say that? Why do I bring up the point that these two are the same in terms of this spontaneous fission? Because it's not the same in plutonium. Okay, so let's go that case. So this second spontaneous, that's the slow burn. If this was open, it would be in a slow burn. Okay, so the Germans knew nothing about plutonium, and that's because this paper, published by this group of people, 3 of the 4 2 of the 4 I knew in this paper, was the discovery of plutonium. And this date here, January 1941, is the date I put in that sequence at the beginning. That's when it was submitted. It was published 5 years later. By the way, this is the first page of the paper. Oh, no, sorry. It's the last page of the paper. No. It's the only page of the paper, and it's only half a page. Okay. This is a superb example of succinct writing. I think our the people at WashU and the administration could take a lesson on how to write. So they wrote this paper, and this little asterisk down here says this letter was received for publication on the date indicated and voluntarily withheld for publication till the end of the war. So the French shut down their publication, we just did. So the Germans did not know about plutonium. That's the guy who really did the work, Art Wall. And this is actually a picture of him in a building that still exists on our campus because he came here afterwards. And actually this place is in one of the labs I work in now. Looks maybe a little bit better, but almost the same. Okay, right now, plutonium, this is a discovery. Started 238. They bombarded it with deuterons. That's 1 proton, 1 neutron, made this, Neptunium-240. It emitted 2 neutrons. They didn't see those. That's a beta decay. Beta minus decay goes to 239. They didn't see that. But what they did see is this alpha decay. Remember, I told you alpha decay is a diagonal, 2 down, 2 over. And they saw this alpha decay. They knew, and they said that this alpha decay, and this alpha decays too. They suspected then that had to be plutonium-238. That was the discovery, but it had nothing to do with making bombs. Afterwards, another paper almost immediately also withheld for publication for 5 years. They exposed 238 to neutrons, and then we also, this is what happened also at WashU. We did this with our cyclotron. And that does a beta decay from uranium-239 to plutonium-239, and another one to plutonium-239. Neptunium, so uranium to neptunium to plutonium-239. And that makes a wonderful bomb. And that started things rolling for trying to get larger quantities of it. That's where the Compton enlisted Mallinckrodt to make uranium for reactors. This is a sketch of the first reactor, human-made reactor in that sustained fission at Chicago. They never took a picture of it. They let it run just for a little while and then they tore it down. This was under in a squash court underneath the Staggs Field at the University of Chicago. Then they moved the operation to what's now Argonne National Lab. And a large fraction of the uranium for that reactor came from Mallinckrodt. And then this one was in Oak Ridge, and this one was in Hanford, where most of the plutonium for the bomb, the second bomb came from. Those reactors worked because they didn't use D2O to moderate the weak carbon, and they got the boron out. The boron, remember in that table I showed you, ate neutrons, so it wouldn't allow the process to continue. So the critical phase thing there was that in the US, Jeremy's crew knew how to get boron, knew that they had to get boron out of carbon. And the person who actually designed the procedure was another person that came to WashU after the war, Herb Potratz. Now, here's the key for the reason for implosion. If you take 238 and expose it to neutrons and go 239 in a reactor, you'll have this process, just like you had in the cyclotrons that were the previous ones. But if you leave it in the reactor very long, you go from 239 to 240. So if this is the time in the reactor, most of the time you create 239, but sometimes the 239 gets a neutron and makes 240. And that's why we need the implosion. And I will explain that now. So the longer in the reactor, the more 240. This gives a list of the amounts of plutonium that were made. Initially, they actually went up an order of magnitude from the first experiment to the next one. This is the deuteron, and this is the uranium, the neutron-induced reaction in the type that ran at WashU, except we had a higher power machine, so we were almost made a 0.5 gram. But that's nothing compared to a critical mass. We needed the reactors to make a critical mass. However, these did not suffer. These were 239. This was 239 and 240. Okay, so there was an issue of the density of plutonium. It has a very complicated material structure, and there was confusion for over a half a year on what the density of plutonium was. It was solved by the same chemists at Los Alamos, and it had a higher. This is the inverse of the density. So this is the alpha phase has a higher density. That means it has a smaller critical mass. In fact, between these two phases, the difference in the critical mass is 50%. They initially thought they were they initially were in these phases. They figured out how to get into the higher density phase. Here I just show you the chemistry scheme that our wall developed. Don't worry about the details, but it is beautifully removes all the contaminants, and this was the guy who discovered plutonium and also figured out how to purify it. Okay, so quickly here, the differences between plutonium 238, that's discovery, 239 and 240. Now I'm putting back on this other valve. And for plutonium 239, that's this one, there's very little spontaneous fission. That means there's no pre-detonation or almost no pre-detonation probability. However, for 240, there is. What's the difference? This one is even odd, and so it has that odd neutron that's blocking the progression down the deformation chain, but this one's not. And so it has about 10 to the 5th times more neutrons just sitting there You're not at the critical mass, you're below the critical mass. The mass could be separated a mile, but there's still fission. Okay. So that required the implosion and so the German effort, why it failed. First of all, the Allies prevented them from getting an easier reactor using D2O because of this. Deuterons can slow down the neutrons, but not eat them up. Carbon looks good and we made it work, but only because we got rid of the boron. The Germans did not get rid of the boron. They had, say, a part per million or many parts per million of boron in their carbon, and the boron, that small contamination, ate up the neutrons and did not allow a self-sustaining reaction. So the Allies prevented them getting D2O. It's a great movie, Heroes of Telemark. Kirk Douglas represents a physicist. This has never looked better. And they never got the boron out of carbon. Okay. And they made a chemistry mistake associated with this boron. And they did not know about plutonium because they kept those publications secret, and the French clamped down on their early success. But they did try. So here is a picture of the German reactor that's just south of Stuttgart. And we went in there, or the Allies went in there, a mission called Alsos. It was Operation Big, which was the invasion of Europe. There was Operation Epsilon, which is a term to mean small, which was a physics-led operation to investigate what the Germans knew. It's called Alsos. They dismantled, this is a picture of them dismantling the German reactor. These are a bunch of people that were in the Manhattan Project and a couple of normal soldiers. They took the bricks, they sent them to be analyzed. Boron it never could have been. Okay, but they did make an attempt. Also, another part of this was that they collected about 8 scientists from Germany, put them in a bugged country house near Cambridge. Actually, they kept them there for almost a half a year. And the bombing of Hiroshima and Nagasaki was a month after this, and they recorded everything they said. So we knew what they knew. The recordings were destroyed. The transcripts were, some of the transcripts were forwarded to General Groves in the Manhattan Project. So there was some attempt. I mean, there were personal things said, and I guess they decided that they didn't want that. They just wanted what they had to say about the bomb, so they didn't keep the transcript. We don't have the. I'm sorry, they didn't keep the recording. Okay. So my summary. Sorry for going a few minutes over. Oppenheimer was a brilliant scientist, theoretician. But that's not what made the Manhattan Project a success. I would say what made the Manhattan Project a success from Oppenheimer's view, or what made Oppenheimer a success in leading it, was his intellectual breadth. He understood atomic, molecular, and nuclear physics. He understood classical chemistry. There was an explosion, a high explosive part of this. He understood that. He understood diffusion and optics. He understood the nuclear chemistry that had to go into it. And he did not stand aloof from the myriad of technical challenges. And he collected with them a group of people that were similarly broad. These are just some of the people I picked out, but these are all very broad intellects. They're not just people that studied one thing and do extremely well. These are people who are interested in many, many topics. And there were these physicists, experimental physicists, theoreticians, and a stellar group of chemists and metallurgists were also mixed in. The Germans individually were fantastic scientists, but I don't think they had this quality that I just mentioned.
and or they were not fully committed. So, I'm gonna stop here. Thank you. Well, I'd love to have your comments and I'll do my best to ask for any questions.
What was Thompson during his time? I see his name was in parentheses there.
Yeah, I put him in parentheses because he was not formally at Los Alamos, he visited. But he was in charge of what was going on at University of Chicago, the so-called Met Lab. And that they were assigned with determining plutonium chemistry, but they were in competition with Los Alamos. I think Los Alamos guys actually beat them on almost every front. And it was a much smaller group of chemists at Los Alamos than there was at Chicago. But they did make contributions to the chemistry and metallurgy. They identified, they said, we don't know, we can't figure out what the density of plutonium is. Yeah, but then the Los Alamos guys said. So he was there, as I said, he was interacting with Mallinckrodt to get the uranium so that the reactors could be built. I can't say how much he was involved at Los Alamos. I don't really know. Mike, maybe you know.
I think he certainly visited there, but he also, had a lot of travel to Oak Ridge and Hanford.
Right, so Oak Ridge, there was another reactor built that was between the one at Chicago and the real production one at Hanford. And that needed the uranium. It was from here. It produced the plutonium that went to Los Alamos. So he was shuffling around between these places and certainly understood the science, but I can't describe a particular piece of science that was due to him.
Is there a story about Mallinckrodt?
Oh, there's huge stories. That's another topic. I don't know if I want to get into that now, but yeah, I could give you a talk on what Mallinckrodt did and didn't do, failed to do, and all the problems, and misinterpretation of the problem. Stuff.
So is that scheduled for?
No.
Is it?
Yeah, I've given it already. Sometime. It's not scheduled.
It's not allowed to have it.
No, it's not on the docket right now. I have given many talks on it, public talks, but not in this form. And for example, there was a forum half a year ago about Jana School, which has been in the news a lot, and I gave a talk there, and there's a tremendous misunderstanding of and the public view of what's going on there is been distorted. That's not to say there's not problems, there is, but the Jana story is generate a lot of confusion. You have a question? Okay.
If we absorbed all this material and understood it, why wouldn't we need a security clearance?
This is all public that I presented. You'd have to know exactly how implosion is, how that works in detail, how the so-called pit decides the shapes, what's inside in detail. This is most, this is easily, material I gave you here is all easily accessible on the web. And pretty, if you take a nuclear class, it's sort of, it's almost elementary, it's clear. And most of this was, a lot of this was known in the very early, without the numbers. A lot of this was known very early in the Los Alamos years. They didn't know the density. They didn't know about the plutonium 240 problem, which just changed things. They were saying, well, maybe plutonium could be gone. We're not sure. Oh, 240 spontaneously fission. Forget that. We have to go this way, which they were already thinking about, but not fully invested in. And they became fully invested in. They knew about the boron here, but not in Germany. They knew about B2O. Germans really woke them up to the importance of B2O, and that's why the Allies had to go in and destroy this plant in Norway. Yeah. If anyone wants to, and the time is getting late, I'll stay here to answer questions, but if people want to leave, they should feel free to get up and go there.
I think you had to kind of straight up where I'm saying. They have the industrial capacity, raw materials. It's hard to figure that out. In enough, in a reasonable amount of time to be for it to be relevant to the work.
Probably not. But, you know, we didn't know that they didn't know about the boron until after the war was completed. So, they had to discover a fission Hahn process. The people that discovered fission, they were in, Hahn was one of the people in Hahn Hall. Heisenberg certainly had a grasp of all the basic science. He got numbers wrong. And he probably wasn't fully committed. But I don't know that. But there are other people in that in the German physics society who are very committed. Von Weizsäcker, von Loh, they were committed Nazis, and if they thought it could be done, they would. In fact, I have some quotes from Von, maybe on the next one. So, so Otto Hahn said, the discoverer of fission, said, if the Americans have a uranium bomb, then you're a bunch of second-rated. Okay, that's what he was telling Heisenberg.
They were even worried that Hahn might commit suicide while he was at Farm Hall because of what happened when they dropped the bomb.
That he should have realized it. But, you know, I don't think it's if you want to peg a failure in the Germans, you wouldn't pin it on Hahn. There's another chemist or experimental physicist, I'm not quite sure which one, Boda, who didn't understand the carbon boron issue, and he should have. He didn't have the Hungarians, he wasn't Fermi, and he missed that point.
The other thing you could say about the German effort was that it was uncoordinated, not like Los Alamos, where everybody was working together and had a goal. These guys were working at cross purposes and even competing with one another. So their effort just wasn't gonna succeed.
But I agree, 100%. But if they knew that the French had almost had a homogeneous reactor, or the real fission cross-section of 235, they might have congealed. They didn't. You're absolutely right. But why didn't they? Maybe they weren't fully committed. They didn't want, some of them didn't want Hitler to have this power. But others, and I mentioned a couple, was because they thought that a bomb would be the size of a city block.
It's fine about now the strong nuclear force. They didn't have really good understanding of strong nuclear forces.
Well, weak is irrelevant. Of course, they didn't have a detailed the kind of understanding we have today.
But what they needed was, provided by this paper by Bohr and Wheeler. And that laid out the energetics. It laid out the barrier. The difference between 235 and 238 was clear. They knew they needed 235, but how to get 0.7% to 90%. They knew nothing about plutonium. So now German, I'm talking about the German. But as far as the detailed strong force understanding, sufficient understanding was there in 1938, 39.
I heard they make H bombs with U-38 surrounding it. It must be effect from past.
Yeah.
Is that right?
Yeah, I showed that in the figure I had. So it's a torrent cycle, if you will. There's an initial fission process, but it's, if you will, spark boosted. They sometimes use the term by DT. And then the energy from that goes into a secondary where there's both fission and fusion going on, and they feed off one another. The neutrons from one can be used for the other, and so forth.
I heard the bomb was covered. I heard the bomb was covered with U-238, and that's where you get most of your blast. Fission on U-238, that's precisely.
So the DT process gives you 14 MeV neutrons. And 14 MeV neutrons is enough of a kick for 238 to get 238 to fission. Okay, so you don't get enough neutron energy in the neutrons from fission to fission 238, but you do get enough energy from the neutrons in DT to fission 238.
Remember when the grandson of War came here?
Yes.
He said that he described some of the conversations of the Germans. I wonder if they described it afterwards, if everything was, destroyed, or if that part like all the British are the honorable for recording that came from where?
Well, the Bohr story has two parts. It has the also part, but there's this famous conversation between Niels Bohr and Heisenberg in a field, open, no recording, but strong impression. And I don't know how much, and there's this famous play that,
Yeah.
so that will be a source of ambiguity forever.
But I always remember that, and they thought, they are not going to record it. No, we can talk to you here.
Well, those two guys, they went out into a field. And Heisenberg must have trusted Bohr not to record him. And anyways, Bohr talked a lot in allegory, so it's hard to understand anything he said.
This one recorded.
What?
This one.
Yes.
Recorded.
They were destroyed.
Yeah. And that point they were saying, I don't know if
No, yes, so there's a quote, there's an exchange there, which they kept and put it in the transcript. Where Heisenberg, which maybe Gerlach, I don't know, one of Diebner. Diebner said to Heisenberg, you think they're recording us? And Heisenberg said, no, they're not that smooth. So that's another mistake, Heisenberg. But the Allies did destroy the actual tapes. They weren't tapes, they were recorded on records. But the actual recordings they did destroy for whatever reason. You can read many things into that. I don't know what the truth is, but the transcripts came to all they are. But the hard facts were when we went and looked at their reactor. And then we knew they could have tried, they did try, they couldn't get it running. They didn't understand why, we understood why. Anything else?
So boron and carbon are right next to each other on the periodic table. Why was boron about 4,000 bonds and carbon sitting at about, what was it, about 35 micro bonds?
Yeah.
That's a hell of a difference if they're sitting right next to each other on the periodic table.
Yeah, so what happens? Can I bring out some chalk? So, you know. Yeah, well, it's finding chalk on here can be hard. So, boron has two isotopes. This one is 20%. Well, boron 10, the other part is boron 11. And plus a neutron goes to lithium 7 and an alpha particle, which everything adds up here. So boron absorbs the neutron, and when it absorbs a neutron, it's north in energy of this decay threshold, of this decay threshold. So it breaks up into these items. So it's a particular channel that's present for boron and a neutron. And in carbon 13, there's no such breakup channel.
Or any of the carbon, I guess, right? There's 13.
Well, I don't, actually, even though I have to look at carbon 13. Carbon 13 is 1%. It must not be that important because it works, but I don't know the number.
Okay. Well, it's basically because it has this decay process.
It has this process, which is determined by the fact that the alpha is well bound. You know, it is effective. We're deep in the weeds here. But it's that reaction. So in fact, if you look it up, the absorption cross-section of boron 10, it says N alpha. N alpha. Okay. Not N gamma or anything else. Come in with a neutron, go out with an alpha. Weeds.
The sensitivity to boron that you've been talking about for the process you're interested in, was so great that techniques at the time were incapable of measuring the amount of boron in the core. One of the things our programs had to do was to develop new methods of measuring the boron so that they could get it down to the measuring. At the current rate of measuring how you can measure it, you could have less than that, you never know.
Right, still make a difference. So the guy who's talking, by the way, knew basically all the chemists that were listed in this talk, and I didn't know her, but just repeat what Al was saying is that this chemist not only devised ways to get the boron out and to know it was out. And that's a huge development. Oh, by the way, if someone asked what was Compton overseeing, what was happening in Chicago, that was happening in Chicago. That was not happening in Fort Valley. Okay, well, have a nice day.
Okay, it does not play a role in the bomb. It plays a role in the reactor. So what happens is you, if you remember the cross-section plot. Here, see, this is a log plot and the probabilities are going up as the energy of the neutron goes down. So you want to slow down the neutron, but you want to slow it down without eating them. So I'm a neutron. I want to bounce off things, but I just want to bounce off. I don't want it to be consumed. If you bounce off boron, you don't bounce off boron, it eats it. If you bounce off hydrogen, there's a little eating. If you bounce off deuterium, it just bounces. It's perfect. It's a thermalizer. It's a slower down, and the cross sections increase as you lower the energy of the neutron. The way, actually, the so-called can-do reactors, the Canadian reactors are all D2O, and they have uranium, and they're enclosed in titanium, but around them is deuterated water. And also important is oxygen is also has a very low number. So D2O in aggregate just serves as a moderator, a slower down of the neutrons without consuming them, so you can have high K. That's what deuteron does. Yeah, they bounce off and come back. Well, that's right. The boron absorbs them. The cadmium absorbs them. So if you want to, it's a right. It's not. It doesn't consume them here. It doesn't all of these things. Hydrogen, deuterium. Whoops. Hydrogen, beryllium, deuteron, beryllium, carbon, oxygen are all good slower downers. It's called moderating the energy of neutrons without consuming them. If you have any of these in there, you eat the neutrons. You just and prevent it from initiating another cycle. So a little of these shuts it down. These are okay.
But the Germans obviously understood that.
No, well, they understood. No,
The heavy water.
they knew this number was small as a
Stable.
right as a yes. They did not know their carbon had. They didn't know this number for boron. The difference between carbon and boron is 6 orders of magnitude. 6. So it doesn't take much boron to pollute carbon. So carbon is good all by itself. So if you want to get pure graphite, there's lots of grades, but there's one that's better than everything by a mile. That's reactor grade. It's not radioactive. It's clean of anything that has a high neutron absorption process. And boron and carbon and boron, that's right. And it's there in all graphite. Dig it up out of the ground, simple refining. Boron is there. At the, I don't know, maybe part per thousand level, maybe many parts per million, but you got to be below parts per million.
So then the control bars are made probably. The
Excuse me?
control bars in reactors are made
Yes.
probably of these things.
They can either be made of boron or better cadmium.
Remember in Argentina, they have like pellets of very, very synthetic kind of material in rods, okay?
The control rods will either have boron or cadmium.
One other thing, just short, Argentina. When I studied nuclear physics
Thank you,
there.
excellent talk.
Thank you.
Sorry.
There is one next week.
Okay, excellent.
Yeah, when I studied nuclear physics, they call the binding energy equation one bisector.
Yes,
I don't know if it-
that's that
the
concept.
Argentinians were not Nazis, we call it like that here also, or?
Well, yeah, von Weizsäcker. And his father was a big Nazi party chief.
That
Yeah.
family was Nazis top to bottom.
Yeah.
And he definitely, when Bohr and Wheeler published their paper, he understood it completely, 100%.
Yeah.
There was no doubt.
Right.
Same with Heisenberg. This was crystal clear what was going on. When Meitner relayed her discussion, understanding to Bohr, Bohr's response was, "Oh my God, we've been fools."
Right.
It was so obvious.
Yeah.
Anyone who was in this game, they knew instantly what was going on. Fermi knew his mistake
Mhm.
right away when Lisa Meitner
Yeah.
published her result. He knew he had made a mistake. He still accepted a Nobel Prize, but
It's
knew-
sad that Lisa Meitner has so many trouble afterwards. I mean, to get a job. I mean,
well, she was a woman and a Jew.
yeah, it was terrible. Terrible. Her nephew didn't have as much of these problems as
Frisch?
she did. Yeah, Frisch.
Yeah, I don't know what happened, what ultimately happened to Frisch.
I don't know, but
But,
she had, I remember she had a lot of trouble, and she had to work like a nobody in whatever Sweden.
She
where
was
worked.
brilliant,
Yeah.
no doubt about it.
Okay, thank you very much.
Sure, hope you enjoyed it.
Yeah.
We were talking about intellectual drought. Isn't it that one?
Did I spell it wrong?
I think you're missing a D.
Oh, I forgot the D. Yeah, you're right. Sorry, thank you.
That's the boron in your pitch.
Yeah, sorry, I was
I
corrected.
enjoyed the lecture. Thank you.
The other reason that, you don't.
I read
need-
Dark's son, the alarm clock design they were talking about was, I remember reading Dark's son, talking about the alarm clock design. What is that? Can you explain it to me a little bit?
I don't know what we're talking
Yeah.
about.
Richard, you read the book Dark's son about building the hydrogen bomb?
Yeah.
It's no.
The guy who did that
They
book about
did
the
have a
first about
student
building the
in
atomic bomb.
college that wrote a
Yeah.
He
paper
mentioned something
like
called an
this.
alarm clock
And
design.
when they handed
I
out
don't know if you'd
the
heard of it.
grades,
Uh,
he didn't get his paper back.
Well, there was
They
a
said
timing in the
twice.
implosion,
It was
Yeah.
back in the
but
50s. Well,
so there was a
60s,
clock
actually.
involved there.
So you
Maybe that's what they were
don't
talking
too much.
about.
Yeah,
I was the
Can't
design,
have
it's
this
called the
back.
alarm clock. I just-
You get an A in the class, but no
You've
paper.
read the book Dark's son, haven't you?
yeah, okay, so I don't know what the clock was referring to there.
Oh, okay, I saw that. Thanks. Great. Look.
I got so many ideas for future sessions like this. I think nobody, you're the only one who's really mentioned the chemists. But we never went into it. What did Kirsty actually do?
So
It was no joke.
no, he ran, in the end, he ran the implosion part.
He had to implement von Neumann's theorem.
Right, or lenses.
And that theorem alone is fascinating because
Did you know him?
I know what it says.
No, did you know him?
Who?
Kiskowski.
Yes,
Oh, because at Harvard, he went back to
yeah,
Harvard.
he was not only at Harvard, but he was, the building we were in, there's several buildings. This is a small building, it had only 2 research groups in it. Nope. Plus, and Kirsty was one, they were working on explosions. Fast reaction. And
Wait a minute, sorry, I have to stop this because we're still recording.
my research director was in the same building, so actually my lab was right across from Kirsty's